This one is a bit more difficult. You just have to think about what the question is asking you. Alright? The Earth is not a uniform sphere, but has regions of varying density. So it says 3 regions. So let's draw all those regions. Alright? And I'll try to make this as nice as possible. It's a bit asymmetrical, but it'll suffice. Looks a bit like an eyeball, but that's okay. So it says use the model given above to predict the average density of the entire Earth. And average density is given by mass over volume. Alright? So because density is constant, we say that density is given by mass over volume. Obviously in this case, density is not constant, so the average density will be given by the mass over the volume. Alright? So for this, we'll need to consider each of our 3 regions. We'll need to consider the total mass, and we'll need to consider the volume of the whole Earth. Alright? So first of all, let's find this V here. Okay? This V is the total volume, which I'll call VEQ. So that's the total volume of the Earth. And the volume of a sphere is given by 4/3 pi r cubed. And in this case, the r is this r, right? Because this is the outside edge of our model of the Earth, right? So this is this here. This distance from the center of the Earth to the edge is the REQ. So we know that this is our that's our REQ. So let's leave this behind for now, and let's look at finding the M. This M here. So this M, it can be given. M can be given by rho times V. This is the average density. But in this case, we have 3 shells, alright, which will give us 3 different masses. So if we can find the total mass by saying M EQ, we're saying EQ for anything where we're finding the total of something. MEQ is equal to M1 plus M2 plus M3. Alright? And let's say that here, well, let's expand this out a bit more using this formula here. So that means that MEQ is going to be equal to rho 1 V1. Let's just do it like that. V1 plus rho 2 V2 plus rho 3 V3. And here, this radius that we're given is not okay. Well, first of all, we have our rho 1 here, rho 2, rho 3. But this V, this R here is not V1. This is R. This is our radius, alright? So this is okay, we have to break this down a bit more, because this is indeed R1, but this is R2 and this is R1. So this is actually R2 minus R1, and this is R3 minus R2. Alright? So here we're not going to consider the whole sphere, but we actually have, so if you have, for example, a sphere like this, and you have a hollow center, then the volume of the sphere is given by, well, well, the volume of the shell, this shell here, which I'm highlighting in blue, the volume of this shell is given by, well, it's the outside sphere minus the inside sphere. Alright, so the outside sphere is 4/3 pi r1. Well, just for consistency, since you're saying the outside sphere is, well, we're saying as we go up, we're going up through the numbers. So the outside sphere is r2. Alright, and the inside sphere is r1. So this is 4/3 pi r2 squared minus 4/3 pi r1 squared. And we can factor out the 4/3 pi, and we will get v shell, let's call it v shell. We get v shell is equal to 4/3 pi and then r2 squared minus r1 squared. Alright? So here we are expanding this out, m eq, and we're saying that v1 is equal to 4/3 pi r1 squared. v2 is equal to 4/3 pi. Now remember, this is this shell over here. Alright? And this is r1. Oh, well, this is r1. And this is r2 minus r1. Alright? So this is 4/3 pi r2 minus r2 squared minus r1 squared. Alright? And here v3 is equal to 4/3 pi r3 squared minus r2 squared. Alright? So for our MEQ equation, we're going to multiply all of these by row 1, row 2, row 3. So row 1 times v1, should be capital V, is equal to row 1, I'll try to color code this, row 1 4/3 pi r1 squared plus row 2 4/3 pi, and then we have r2 squared minus r1 squared, and then plus row 3. I'll try to move this down a bit, actually. Row 3 and r3 squared minus r2 squared. So that is MEQ. So in our, when we have here the density, the average density is equal to the total mass divided by the total volume, we have our total mass. So we can put that in there. Alright? So I'll skip through this. So this divided by the, we said the total volume was equal to 4/3 pi r3 squared. And now we can cancel out. Hopefully you can see that 4/3 pi cancels out. So we are left with our row average is given by row 1 r1. Sorry, these all should be cubed. Now that's a big mistake. But if you're following along with the video, it shouldn't be too bad of a mistake to figure out, because we're talking about volume here, the volume of the sphere, right? So rho 1 r1 cubed plus rho 2 r2 cubed minus r1 cubed plus rho 3 r3 cubed minus r2 cubed divided by r3 cubed. And you can just go ahead and plug in these values, and you should get an average density, which I'm going to plug in right now. Alright, so I put everything into my calculator, and I'm getting an average density of around 5.5 times 10 to the third kilograms per meter cubed. I don't know if the number is exactly correct, but the important thing is the process. And that's almost a 10-minute process to get there. And if you can do that, B is easy. Now we just take R. Let's see. We know that the actual mass of the Earth is 5.98 times 10 to the 24th. So, writing with my highlighter again. We know that the actual mass of the Earth is 5.98 times 10 to the 24 kg. Let's just call it M for now. And the actual radius is 6380 kilometers. And it just says compare the actual average density to the one that we have calculated using our model. So here, same thing. Just go ahead and multiply the mass, divide the mass by the volume. And here the mass is given. The volume is 4/3 pi r cubed. And if you plug in these numbers, I've actually already done it. If you plug in these numbers, you'll get 549 or 7 kilograms per meter cubed. And then once you find this value here, all you have to do is divide it by this value to get the percentage difference. And that's a lot of work. This is probably not going to be like anything you get on the exam, but it's good to understand the concepts. All right, last problem here. Actually, the calculations are quite simple. The concepts can be difficult. That's why I've chosen this. It's a bit unintuitive. All right, so in this pipe here, which I'm gonna try to get a decent drawing of. Let's imagine first that there's water filled up to a certain amount. All right, you know that they have to be at the same height, right? Because there's equal pressure pushing down on both sides, just atmospheric pressure, right? So as long as they're both sides of this U-shaped pipe is open to the atmosphere, they've got to be at the same height, and at the same height, they will have the same amount of pressure. Okay? Now, let's consider that to one side of the pipe, oil was added. All right? So there we have our water. And up here, there's oil, and there's a height distance. Well, let's use the exact numbers that they use, right? So the height of the oil to the water is 27.2. The height of the water to the same height here, which we'll call this h is equal to 0. The height there is, well, there's a height difference of 8.62 centimeters. Always include the units, centimeters. All right. So again, you have to remember that atmospheric pressure is pushing down on both of them. That means at the top of the liquids, which is up here, just up here for oil and down here for water, pressure is the same because the atmospheric pressure is the same, and that's pushing down on both sides of the pipe. Okay? So let's say let's use this pressure here. Let's call it P oil, okay? P oil is defined by rho of the oil times G times H. And for H, I'm saying that this is H equals 0 down here. Down here is H equals 0. So this is actually a height of, we can use negatives. It doesn't really matter. This H equals 0 is completely arbitrary. It's like choosing your potential energy 0 point. Alright? And we can say it's negative. I'm just going to say it's positive. It makes calculation a lot easier. You'll see that it doesn't really matter. But let's just say that H is equal to 27.2. Alright? So that's the pressure of the oil. And now, let's find the pressure of the water. Okay? Now that's equal to the density of the water times G times H. And here, H is this distance, alright? Is equal to 27.2 minus 8.62. Well, this is H oil. This is H water. So 27.2 minus 8.62. I'm just gonna do this real quick. Alright, I got that H water is equal to 19.58. I don't know if that's right. I just kind of quickly did it in my head. Well, it should be 19.38 actually. 19.38. So we have our pressure of the oil at the top of the pipe, and we have the pressure of the water at the top of this side of the pipe. And again, the atmospheric pressure is the same on both of them. Alright? So the pressure at both of those points, okay, P oil and P water, the pressure is the same. So we can equate them. So rho oil times G times H oil is equal to rho water times G times H water. Now we are trying to find the density of the oil. So let's solve for that. First of all, G's cancel. Divide both sides of the height of the oil, and we get rho oil is equal to rho water H water divided by H oil. And remember, usually they'll tell you that density of water is equal to 1,000 kilograms per meter cubed. But even if they don't, it's something you probably should know. But they'll probably tell you. But anyways, you substitute all of that in. We have H water is 19.38 times 1000 divided by H oil, and you'll get a density that is, well, it should be a bit lower than raw water. I'm just gonna do it to make sure. All right, and you should approximately get around 708.8 kilograms per meter cubed. Now, I hope these problems are tricky. I hope these videos help you a little bit with them. If not, you can ask me in person, and I'll talk about it in more detail. Well, yeah, have a good evening.